It works on my machine. 4 words that have started more arguments between developers and operations than almost anything else in software. You build something, it runs perfectly on your laptop. You ship it, and it immediately breaks on the server. Different operating system, a missing library, the wrong version of Python, an environment variable nobody documented. Hours vanish hunting a problem that only exists because your machine and the server aren't the same machine. Docker made that entire category of problem disappear, and it did it so well that by 2026, nearly 3/4 of all professional developers use it. Welcome back to DevWise. Today, the most useful, most universal skill in modern software: containers. What Docker actually is, how it works under the hood, and how to package your own app so it runs identically everywhere: your laptop, your teammates, and production. If you build software, this one's for you. Let's begin. Let's start with the problem, because Docker only makes sense once you feel the pain it removes. Every application depends on more than its own code. It needs a particular language runtime, Python 3.12, or Node 20, or Java 21. It needs libraries at specific versions. It needs system packages, environment variables, configuration files. All of that together is the application's environment, and here's the catch: that environment is almost never identical between where you build the software and where you run it. Your laptop has Python 3.12, the server has 3.9, you installed a library last month and forgot. The server never got it. Your machine sets a time zone, the server doesn't. Each difference is a tiny landmine, and the more machines your software touches, the more landmines you plant. This is why it works on my machine is simultaneously true and useless. It does work on your machine under conditions that exist nowhere else. The old answers were all painful. Write a document listing every setup step. Nobody keeps it current, and humans make mistakes. Use a virtual machine, a full simulated computer, for each app. That works, but it's enormously heavy. Every VM carries an entire operating system, gigabytes of it, booting for minutes, consuming memory just to idle. Running 10 apps meant 10 complete operating systems stacked on one server. Wasteful, slow, expensive. Docker's insight was to ask, what if we could package an application with everything it needs to run: its code, its runtime, its libraries, its configuration, into a single, sealed, portable unit, but without dragging along an entire operating system each time? What if that unit ran identically on any machine that has Docker, because it carries its own world with it? That sealed, portable unit is a container, and it turns out that idea changed how the entire industry ships software. To really understand containers, compare them to the thing they replaced: virtual machines. This one diagram is worth more than any definition. A virtual machine works by simulating an entire computer in software. On top of your real hardware sits a hypervisor, and on top of that, each VM runs a complete guest operating system, its own Linux or Windows, kernel and all, and your app runs inside that. So 3 apps means 3 full operating systems, running simultaneously, each 1 gigabyte in size and taking minutes to boot. VMs are strongly isolated and genuinely useful, but they are heavy in every dimension: disk, memory, and startup time. A container is fundamentally lighter because of one clever trick. Containers share the host's operating system kernel, instead of each bringing their own. On your hardware sits one host operating system, then Docker, and then your containers, each holding just the app and its dependencies, but not a whole OS. They're isolated from each other, so one container can't see into another, but underneath, they're all sharing the same kernel. The result is dramatic. A container is often megabytes, not gigabytes. It starts in milliseconds, not minutes, and you can run dozens on a machine that would groan under a handful of VMs. Here's the analogy that makes it stick. A virtual machine is like a housing development, where every home is a separate, detached house, its own foundation, its own plumbing, its own roof, complete isolation, but you rebuild everything for each home. A container is like an apartment building. Each apartment is private and self-contained, with its own locked door, but they all share one foundation, one set of utilities, one structure. Far more homes on the same land, built far faster because you're not duplicating the foundation every time. One honest caveat, because accuracy is the brand. That shared kernel means containers are slightly less isolated than VMs. Their processes on a shared operating system, not fully separate computers. For the vast majority of applications, that trade is overwhelmingly worth it. Near VM isolation, at a tiny fraction of the weight. And when you truly need hard isolation, you can run containers inside VMs and get both, which is, in fact, exactly what most cloud platforms do for you. Now the two words people mix up constantly, and getting them straight is the moment Docker clicks: images and containers. They are not the same thing, and the difference is simple once someone says it plainly. An image is the blueprint. It's a read-only package containing your application and everything it needs. A frozen, complete snapshot of an environment, sitting on disk, doing nothing. A container is a running instance of that image. When you tell Docker to run an image, it takes that blueprint and brings it to life as a live, running container. The relationship is exactly like a class and an object in programming, or a recipe and the meal. One image, the template, can spawn many identical containers from it, build the image once, run 100 containers from it, all identical. Now, the genuinely clever part, how images are built, because this is where Docker's efficiency comes from. Images are made of layers, stacked on top of each other. Each layer is a set of changes. This layer installs the operating system basics. This one adds Python. This one copies in your code. This one installs your libraries. Stack them, and you have the complete image. And here's why that matters. Layers are cached and shared. If 10 different images all start from the same Python base layer, that layer is stored once and reused, not copied 10 times. When you rebuild your app after changing one line of code, Docker reuses every unchanged layer from cache and only rebuilds the ones that actually changed, turning a rebuild that could take minutes into one that takes seconds. That layer model is also why Docker is so fast to share. When you download an image, you only pull the layers you don't already have. Pulled a Python base for one project, the next Python project reuses it instantly. It's deduplication, built into the core design. And where do these images live and travel? In a registry, a library of images you can push to and pull from. The default public one is Docker Hub, which hosts hundreds of thousands of ready-made images, official, trusted images for Python, Postgres, Redis, Nginx, and almost anything else. This is a quiet superpower for beginners. You rarely start from nothing. You start from an official, battle-tested base image and add just your part on top. Companies also run private registries for their own internal images, but the model is identical. Push an image up, pull it down anywhere. Let's make it real by packaging an app ourselves. The recipe for an image is a plain text file called a Dockerfile, and it's genuinely readable. Each line is an instruction, and most instructions create a layer. Let me walk through a real one for a Python web app. From Python 3.12 Slim. Start from the official Slim Python image. That's your base layer, and it means you never install Python by hand. Work dir/app. Set the working directory inside the container. Copy requirements.txt. Copy just your dependency list in first. Then run pip install those dependencies. Notice we copy the requirements file and install before copying the rest of the code. That's a deliberate, powerful trick. Because layers are cached, if your code changes but your dependencies don't, Docker reuses the cached install layer and skips reinstalling everything. That one ordering choice can cut your build times dramatically. Then copy ... Copy your actual application code in. Expose 8000, document that the app listens on port 8000, and command, the command that runs when the container starts. Here, launching your app. That's a complete, production-shaped Dockerfile in 7 lines. Now you build it. Docker build -t to name it DevWise app, and a dot meaning use the Dockerfile here. Docker reads your instructions top to bottom, creating each layer, caching as it goes. Then you run it. Docker run, and here's a crucial flag, -p 8000:8000. That's port mapping, and it trips up every beginner, so let's be clear. A container is isolated by default, including its network. The app inside is listening on port 8000, but that port is sealed inside the container. -p 8000:8000 connects port 8000 on your machine to port 8000 inside the container, opening a door so you can actually reach the app in your browser. Without it, the app runs perfectly and you simply can't get to it. The number one why can't I connect confusion for newcomers. And that's the whole loop. Write a Dockerfile, build an image, run a container. The same 3 steps whether you're packaging a tiny script or a service that'll run on 1,000 servers. 2 more concepts turn Docker from a toy into something you'd actually run, and then 1 tool that ties it all together. First, data, and a fact that surprises everyone. Containers are ephemeral. When a container is deleted, everything inside it vanishes, by design. That's wonderful for the app itself, which you want fresh and identical every time, but it's a disaster for a database, where the whole point is to keep the data. The answer is volumes, storage that lives outside the container's lifecycle, on the host, and gets mounted in. The container comes and goes, the volume and your data persists. Rule of thumb worth memorizing: if you need to keep it, it goes in a volume, never inside the container itself. Second, briefly revisited because it matters so much, ports. We saw port mapping open a door into one container. In the real world, you have several containers, an app, a database, a cache, and they need to talk to each other, and selectively to the outside world. Docker gives each a private network where they can reach each other by name, while you expose only what the public actually needs, which raises an obvious problem: managing an app container, plus a database container, with its volume, plus a cache, each with its own run command and flags, by hand, is tedious and error-prone. That's what Docker Compose solves. Compose lets you declare your entire multi-container application in one YAML file. Every service, its image, its ports, its volumes, how they connect, and bring the whole stack up with a single command, Docker Compose up. Here's a real one: a web service built from our Dockerfile, and a Postgres database with a volume so its data survives, wired together so the web app can reach the database by name. One file, one command, and your whole application environment stands up identically on any machine, which is the original promise of Docker, now scaled to entire systems. For local development especially, Compose is the tool you'll reach for every single day. One security note, since it's a common beginner trap: never bake passwords directly into an image or a Docker file. Anyone who pulls the image can read them. Pass secrets in at runtime through environment variables or Docker's secrets mechanism. As the example hints, your image should be safe to share. Your secrets should never travel inside it. Now the mistakes, because Docker is easy to start with and easy to misuse, and knowing the traps ahead of time saves you weeks. These are the ones I see again and again. Mistake 1. Gigantic images. It's easy to build a 2 GB image by starting from a full operating system and installing everything. Huge images are slow to build, slow to push, slow to pull, and slower to start. The fix is discipline. Start from a slim or minimal base image. That slim tag we used is doing real work. Install only what you need, and for compiled languages, use multi-stage builds, where you build in one big image but copy only the finished result into a tiny final one. A lean image isn't a nicety. It's faster and more secure, because there's simply less inside it to go wrong or be attacked. Mistake 2. Running as root. By default, processes in a container run as the root user, and if an attacker ever breaks out of your app, root inside the container is a far bigger problem than a limited user would be. Good images create and switch to a non-root user. It's 1 or 2 lines in your Dockerfile, and it meaningfully shrinks your risk. Mistake 3, which we flagged, and it bears repeating because it's so damaging: secrets baked into images. A password, or API key, written into a Dockerfile, is now permanently in that image's layers, readable by anyone who pulls it, and pushing it to a public registry leaks it to the world. Secrets come in at runtime, never at build time. Mistake 4. More mindset than command, treating containers as pets. The whole philosophy of containers is that they're disposable, cattle, not pets, in the old ops phrase. You shouldn't be SSHing into a running container to fix it by hand, because the moment it restarts, your fix is gone and you're back to configuration drift, the exact problem we fought in every episode. If something needs changing, change the image and redeploy. A container should be something you can kill and recreate without a second thought. Internalize that, and you're not just using Docker, you're thinking in containers. Let's land it with the habits that take you from Docker works to Docker works well, the difference between a beginner and someone who clearly knows what they're doing. 1. One process, one container. Resist the urge to cram your app, your database, and your cache into a single container. Each service gets its own, and you compose them together. This keeps each piece simple, independently scalable, and easy to reason about. 2. Keep images lean. Slim base image, only what you need. Multi-stage builds for compiled languages. Every megabyte you don't add is faster builds, faster deploys, and a smaller attack surface. 3. Never put secrets in an image. Runtime injection, always. Your image should be safe to publish to the world. Assume one day it will be. 4. Order your Dockerfile for the cache. Copy dependency files and install before copying your code, so a code change doesn't trigger a full reinstall. This one habit will save you more waiting than almost anything else. 5. Treat containers as disposable. Persist data in volumes, never inside the container. Don't handfix running containers. Change the image and redeploy. Cattle, not pets. Master those 5, and containers stop being a mysterious bit of DevOps magic and become what they truly are, the simplest reliable way ever invented to make your software run the same everywhere. It works on my machine becomes it works on every machine, because now it's the same machine everywhere it goes. That's Docker. The problem it kills: containers versus virtual machines, images and layers, your first Dockerfile, data and compose, and the mistakes to skip straight past. Learn this one skill well, and you've unlocked the foundation nearly all of modern software delivery is built on. If this earned its 20 minutes, a like genuinely helps the channel reach more engineers, and subscribe for more calm, practical guides for the people who build and ship. Plan before you apply. Goodbye for now.